In this video, we're going to talk about differential representations of signals, which is a way to break signals up so that we can think about their difference separately from their average value. I've put a pair of signals on this slide and labeled them v1 of t and v2 of t. This drawing is called the single-ended representation of signals. There are two signals, and we have a function representing each of them. As a side note, I've picked these two signals because they make a good picture. Any arbitrary pair of signals would work fine for the analysis that we're going to jump into. We can also make a differential representation of these signals. The differential representation is made up of two signals, a common mode, which is the average of the two single-ended signals, and a differential mode, which is the difference of the two single-ended signals. And again, this works for any pair of signals. We can find an average and a difference between any two things. For instance, you might have noticed that I use total signal notation for the common and the differential mode. And that's because these don't need to be small signals. They also don't need to be in the midband. So we're not dependent on the size or the frequency of the signals when we do this analysis. This is how the common mode and differential mode might look on this drawing. The common mode is the average of the two signals, so it sort of snakes in between them. And the differential mode would be the difference between these two signals. I've only shown that at one point here as this vertical line, but you can imagine that vertical line sort of getting bigger and smaller as we swept it across this pair of signals. If we plotted the differential mode out, it'd just look like another sine wave. I thought this was a clearer way to indicate its value. It's possible to invert the differential representation of equations, so you can express the single-ended values in differential terms. So for instance, v1 is the common mode plus half the differential mode, v2 is the common mode minus half the differential mode. One subset of this differential representation is purely differential signals. Those are signals where the common mode is a DC value. Which I've indicated with the total signal notation here. The total common mode signal equals the large signal DC value. One byproduct of that means that when one of the different single-ended signals swings up, the other one has to swing down so that their average stays the same. So purely differential signals are always swinging in opposite directions. Here's some practice with the differential representation. I've drawn a pair of signals on the left graph. I'd like you to pause the video and try to draw their differential and common mode representation on the right. The common mode is at 0.2 volts most of the time because both the left V1 and V2 are 0.2 volts. But when either V1 or V2 increases to 1.2 volts, the common mode signal jumps up to 0.7 volts. It picks 0.7 because that's halfway between 1.2 and 0.2. The differential mode signal jumps up to plus 1 volt when V1 increases and minus 1 volt when V2 increases, and that's because the differential mode is given by V1 minus V2. This signal, by the way, isn't purely differential because the common mode voltage changes. So in summary, any two signals have a differential representation, where the two single-ended signals v1 of t and v2 of t can be represented as a differential mode and a common mode. And purely differential signals, which are sometimes just shortened to differential signals, have the common mode equal to a DC value.